Hi, I'm Jonathan Glesser. This is the intro into trigonometric ratios. In this video, we will give definitions of three trigonometric functions, namely the sine, cosine, and tangent functions. Additionally, we will try to provide some motivation for these definitions, give a mnemonic for remembering them, as well as give an example of using the mnemonic. We will assume basic properties of similarity. Specifically, if we have a triangle with known side lengths, then the ratios of those side lengths do not change if we scale the triangle. Consequently, given any right triangle, we can divide all sides by the length of the hypotenuse to obtain a similar right triangle whose hypotenuse has length 1. Our second assumption is that the angles of a triangle add up to 180. Since a right angle has measure 90 degrees, the measures of non-right angles in a right triangle must sum to 90 degrees, and thus they are complementary. Let's assume we are given a right triangle and that we have scaled it so that the hypotenuse has length 1. We will fix the measure x of one of the non-right angles as in the picture. The side opposite to x looks like a little pole, the kind you might put a sign on. So we label the height of this pole, i.e. the length of the side opposite to x, as sine of x. If we now scale the triangle to have a hypotenuse of arbitrary length h, then the side opposite x will scale to have length h times the sine of x. This leads us to our main definitions. First, given a right triangle in a non-right angle of measure x, we label the side opposite x by O, the side adjacent to x by A, and the hypotenuse by h. As we saw previously, O equals h times the sine of x. Therefore, sine of x equals O divided by h. If we denote by y the complementary angle to x, then the same reasoning as above implies a equals h times the sine of y. However, we would like to define the length a completely in terms of x. As y is the complement of x, we know that y equals exactly 90 degrees minus x. So we define a new function, the cosine, which equals the sine of the complementary angle. We abbreviate cosine to cos, and note that the co in the beginning is a reminder that the relationship to sine is given by complementary angles. A third useful trigonometric function is the tangent function. The tangent of x is defined as the slope of the hypotenuse when viewed as traversing from the vertex corresponding to x to the vertex corresponding to y. This slope is computed by finding the ratio of the rise to the run, that is, by computing the ratio of the length of the side opposite to x to the length of the side adjacent to x. In short, the tangent of x equals O divided by A. Equivalently, the tangent of x is the ratio of the sine of x to the cosine of x. While the best way to remember all of these new functions is to learn where they come from, in the heat of battle it is probably convenient to have a quick mnemonic for remembering everything. The classic mnemonic is the acronym SOHCAHTOA. Here, each of the letters stands for a word. Written out in full, we get the following chart, which you should read in triplets. The sine is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse. And the tangent is the opposite over the adjacent. So let's do an example. We will compute the sine, cosine, and tangent for angles x and y in the given right triangle. First, to compute the sine of x, remembering the SOH part of SOHCAHTOA, we find the ratio of the length of the side opposite to x to the length of the hypotenuse. The opposite side has length 5, and the hypotenuse has length 13. Thus, the sine of x equals 5/13. For y, the opposite side has length 12, and therefore the sine of y equals 12/13. Next, to compute the cosine of x, we remember the CAH part of SOHCAHTOA, adjacent over hypotenuse. The adjacent side to x has length 12, and the hypotenuse has length 13. Hence, the cosine of x equals 12/13. For y, the adjacent side has length 5, and therefore the cosine of y equals 5/13. Alternatively, we could have remembered that the cosine is the sine of the complement and transposed our answers for sine of x and y. Finally, to compute the tangent of x, we remembered the TOA part of SOHCAHTOA, opposite over adjacent. For x, the opposite side has length 5, and the adjacent side has length 12. Hence, the tangent of x equals 5/12. For y, the opposite side has length 12, and the adjacent side has length 5. Thus, the tangent of y equals 12/5. A fun observation is that the tangent of y equals the reciprocal of the tangent of x, the complementary angle to y.